Okay, folks, welcome to our introduction, introducing the concepts on lesson 15.3, our last lesson, exponential and logarithmic equations and models. So this is an important aspect of our work. Now I call this the log one-to-one properties. So notice this log base 2 of x is equal to log base 2 of 5. What can we conclude? That the x has to equal 5. Here's another property. Log base x of 3 is equal to log base 5 of 3. Well, if the numbers are the same, what can you say about the bases? They would have to be the same too. So x is equal to 5. Now, how are we going to do this problem? Well, one way to do it would be to change this to a log. This would be log base 7 of 20 is equal to x. And now we could use a change of base rule. That's the same thing as log of 20, that's log base 10. Log of 20 over log of 7, put it in our calculator. Okay, another way to do that problem is to take the log of both sides. If I take the log of both sides, the common log that is, notice I could use the power rule. If I use the power rule, then I could just move that x to the front. It's just x times some number, and I just divide both sides by log of 7, and lo and behold, I have that answer. Notice this answer matches that answer. So keep that in mind. This problem is a little more sophisticated. I'm going to have to take the ln of both sides, right? Because I have that base e. I'm going to take the ln of both sides. Now, I could still do that same thing. I could move this to the front, which is 3x plus 1 times the ln of e is equal to the ln of 18. But wait a minute, we should all know now that the ln of e, that's a property. That's log base e of e. That is 1. That is equivalent to 1. So 1 times that is equal to ln of 18, or 3x plus 1 is equal to the ln of 18. Subtract the 1 and divide by 3. Subtract the 1 and divide by 3. Ln of 18 minus 1 divided by 3. Now make sure when you put this on your calculator you do that, then you hit the divide sign. And again, you could put that in your calculator, find out what the number is, and put it back in the beginning and see if that works. Okay, this is from the first reading, example 6. Now this seems like such a complicated problem, but really it's not too bad. Log base 2 of 2x minus 5 minus log base 2 of x minus 2 is equal to 0. I can move that to the right side. That would be log base 2 of 2x minus 5 is equal to, let's move that to the other side, log base 2 of x minus 2. Now notice these two parts are the same, so the arguments would be equal to each other. Or 2x minus 5 is equal to x minus 2. This goes back to like the first week. Remember, move the 1x over here, so subtract 1x. Okay, so x minus 5 is equal to negative 2. Add the 5. All right, 5 and a negative 2 is a 3. How do you know that's right? Plug that back in and see if it works. You really do need to check your answers when you're working with logarithm. Now this looks like it's a hard problem, but really it's not that bad. I call this if the window gets shut, open a door. Now it is very hard to get into that argument right there to find x. So you just can't multiply and divide things. We're sort of stuck right now. But this is a log form. Let's see if we can move it to the exponential form. Okay, the base is 3, the power is 2, and the number is 2x minus 5. Now you see how important it is to know that information? Okay, let's fix this up. It's not that bad. Okay, let's add the 5, so that's 14, and divide by 2, so x is 7. Okay, so if I put a 7 in there, that's 14 minus 5 is 9. Log base 3 of 9 is 2, because 3 squared is 9. Okay, now we're just going to take a little break from working equations to go over some properties. Let's take a look right here. Log properties. Log base b of b is what? It's really asking b is what power of b? Well, b is just b to the 1, so the answer is 1. What is log base b of 1? In other words, b to what power gives me 1? In other words, look, b to what power gives me 1? And we know that's 0. Okay? Now the same thing's true over here. Ln of e, or log base e of e, that's 1. And ln of 1 is 0. Okay? We know that's true because it's true over here. Okay? And that is a particular example. Now, look at this question over here. Log base b of b to the x. You can call this an inverse property. So I have the base, then I have that number is the base to a power. Well, what if that was that? Well, that'd be 1. Okay, what if that was 2? What power of b is b squared? It's 2. So what if that's x? This is just equal to x. All right, just think about it. Put some numbers in here. Now look at this one. B to the log base b of x. What is that? It's probably a little easier to do this. Watch this. We all know that log base 2 of 8 is 3. Now what's 2 cubed? 2 cubed is 8. Oh, I see. It's just, this is the base to the log. They're inverse operations. That's like x plus 1 minus 1 is x. So it's simply the argument. Now, if that's true, what is this equal to? All of that equals to is these bases match just x. Those are called inverse properties of logarithms. Okay, folks, this is an example from your lesson. So 10 log of 46. Now remember, log by itself is just a common log. So sure enough, you could do this on your calculator. You could probably guess what it is. It's just going to be 46. That is equal to 46. All right, how about this one? E to the ln of 7k plus 2. Sometimes it helps when you're doing that to rewrite that as log base e. Notice that this base and this base match up, so the answer is just simply going to be the argument, 7k plus 2. So try to remember that property. You may want to do some more examples to help that to be more clearer to you. Okay, now we're back to the first lesson, example 9. How am I going to find x? Well, the key is that plus sign and your properties of logs. Remember, plus means multiply. So I'm going to take these two and multiply them together. Okay, and that's equal to 1. Whoops, I'm stuck. Okay, remember, if a window shuts, open a door. Just go around it another way. Change it to exponential. What's the base? 2. What's the power? 1. What's the number? It's going to be that multiplied out, which is x squared minus 5x plus 6. Okay, remember this is just 2 right here. All right, could we solve this? We could. This is x squared minus 5x plus 4, and that's equal to 0. I wonder if that there's numbers that would work there. How about x minus 1 and x minus 4? Would that give me my plus 4 and that give me my negative 5x? Now, what are the answers here? The answers is 1 and 4. The answers are 1 and 4. Now, I don't mean to be mean, but answer choice A could be 1, answer choice B could be 4, and answer choice C could be 1 and 4. You may want to pick that one, but you may be wrong. Go back and put these values in your problem. Remember, you can't have a negative argument. Let's put the 4 in there. That gives me a 1. That's okay. put the 4 in here. That gives me a 2, that's okay. But if I put this 1 in here, I'm going to have a negative 1. And remember, the log graph does not even touch the x-axis. You can't have a negative 1 in the domain of a log function. That is called an extraneous answer. So answer choice 4 would be the correct answer. Try to remember that. This problem's a little tedious, so you can do it. You could solve it on your calculator, but I'll show you how to do this problem. Okay, this is how you put it in the calculator. That may help you. And you should get negative 2.87, so forth. Okay, so I took the len of both sides, and I worked that out. Please pause your video so you can see how I did that. Okay, so here's from the second reading, example 1. I have $500, 4.5%, compounded monthly. How much would I have in 3 years? That's the first part. Now, if you notice, that first part was pretty a plug and chug. Here's the formula, plugged them in, cranked my answer out. But the second part says, when will I have $750? See, we're trying to find t. Now, that's going to require us to divide by the 500, then take the log to get into that power position. Okay, notice what I had to do for this problem. I set that up, and then I divided by the 500, and then I took the len of both sides. When I took the len of both sides, I moved that 12t to the front. And so I'm trying to solve for t. I'm going to divide this left side by everything else on the right side. That's this. And put it in your calculator, and you should get that answer right there. Of course, when we say put it in your calculator, we're talking about putting it in this particular way. Okay, that's the only way that you can make it work really good. That's a suggestion. Now here's a problem that seems to get some people. Again, we're in second reading, example 3. Have $200. Here's my interest compounded continuously. When will I make $350? Okay, so here's an answer to that problem. I'm going to have to use the shampoo formula. Okay, so here you go, right here. I'm trying to get to 350, have 200. Remember, that's R as a decimal. I divided. Now I got to get to that variable in the power position. I'm going to take the len of both sides. When I do that, I use that property, okay? And sure enough, that would just be that value there. And then I divide by that value, the coefficient there, and I get 9.73 years. I want to finish up this introduction by talking to you about two important formulas. They have to do with growth and decay. This is the one that's generally used in the field of science. Now, you could apply it in population and say your initial population times E, that's a constant. K is a constant. Normally it's a very small number, very close to 0. So I suggest you round to 4 places or don't round. And then T is normally in years, but it could be minutes or seconds. And then that would be your final population. Okay, we have two problems. One is there's an element with a half-life of 30 years. I'm starting with 50 milligrams. How long till I get to 10 milligrams? Okay, so here's how to work this problem. Remember half-life. 30 years for half. If I started with 50, that'd be 25. 60, that'd be 12.5. I'm thinking 70 years, for us to have 10 left. So here's the formula we're going to use, but I had to find K in order to make the problem work. Now I know if I started with 50 and ended up with 25, it would take 30 years. So now I only have one variable, and this is explaining how I found the value of the K, which is rounded to 4 places, is this number. So then I put it back in the equation. I'm starting with 50. I end up with 10. Here's the K and here's the T. And of course I moved the 50 over. I reduce it to 1 over 5. I take the len of both sides. And then I solve for T. And I have the len of 1/5 divided by that decimal, which is 69.67 years. Okay, this is one way to do example 7 in that second reading. How old is this tool? I use the formula, I find K, I left it in that form, 25% was remaining, I solved the problem, I just left K right there, here's K, I substituted K back in, I got 11,460 years ago. That's called radiometric dating.